Any questions, anybody? I think we're okay.
Okay. So going back into our material here. So another way of doing this, if you really just wanted to change one shader value, it's probably not necessary to do a material mix. Let's just use this, assign this water material to it. And then you remember that we have this attribute that we called speed. And what that means is we can have a value that goes from 0 to 1 based on how fast those points are moving. And that's handy because, well, we can actually just remap that. Just add a material remap. And we know we want anything that's fast moving, anything that has a speed that's not 0, we know that's going to be water. So we can put that into this remap. And so anything that's water needs to have a IOR of 1.33. So (1.52) and 133. So we're remapping that 0 to 1, and we can just put that into the specular IOR. I believe I got that right. Yes. So you can remap any of those values for inputs into the shaders. And if we map the, just we can do a color ramp. And put that into the base color. Since we have transmission, we'll have to turn that down for that to do anything. But this is just to, let's see, turn down transmission. Just to illustrate the things that you can do just by importing importing those geometry attributes and mapping them into your materials to do really kind of fun, like even to do more stylized type of effects. So let's see, I think that's everything I had on rendering. Oh, one more thing. It's going to be handy also, since we have those attributes, I'm just going to map this glass into our shader output. It's going to be handy to have those also in the render for later, for compositing later on. So one thing is, let's say we're not doing something as simple as this martini glass. We have more complex geometry that might have multiple shaders and textures, and we may want to just render that as a separate pass and blend it together in the comp. And the way we can do that is we can just create an extra render variable. So add that, and we're going to name it blend. And we need to, well, the data type is float. And it's called matte blend. And the source type is it's a primitive variable in Solaris speak, primvar. So what that means, it's going to create a new output variable. So now we should be able to view it. And there it is. And in this view, it comes out as red. But if you look at the EXR output in a compositing package like After Effects or Nuke, that will give you basically a matte that goes from black to white. And we can do the same with our, can actually visualize speed just by doing this. Yeah. So you can create any number of arbitrary render variables that are going to be useful to you in the comp. So does that make sense?
Yep.
Yeah,
So basically, you can put in any attribute you set on your geometry and put it there in the variable, and you get a map from it.
that is correct. Yeah, and it doesn't have to be a
Ah.
float either. It can be a vector. It can be
Oh,
any of these data types, and it's super handy when you're doing compositing.
oh, that's really nice. Thanks.
All right. I think that's everything I had on the render front of things. Other than just setting things like you do want to use velocity blur because we're calculating velocity from those points. We're not doing depth of field. Setting your limits obviously is important. Everything else, excuse me. Everything else is fairly default. And then of course, the highest amount of path trace samples that make sense will give you better results, even if you're doing denoising. So if there's no questions, I'll move on from here.
Are you using motion blur with this?
Yes.
Ah, okay. Is
Yeah.
VDB a problem? Because the mesh is changing every frame, right?
Well, back in the meshing step, we're transferring velocities from the original points and
yeah,
meshes
I remember.
to the mesh after it's been gone through the VDB process.
Ah, perfect. Thanks.
Yeah. I think that brings us to the end of this particular part of the.
We do have another motion blur question.
Sure.
Are there any motion blur roadblocks with the setup? Seems to be a common problem with Karma.
I haven't run into anything with that.
Okay.
I think as long as you're transferring your velocities, check to make sure your velocities are there, then you should be good.
Okay, great.
All right. So now I think we can move on to the liquid head section of our course here. And that's in the student files that were posted, that's going to be the 3B. So let's open this. All right. So I'm going to do this in a similar way that we did our first couple sessions, or the second one actually, where I actually have it all kind of laid out and built here, and I'm going to redo it step by step here on a blank canvas, so to speak. So the idea, actually, let me play this back. So we're using the same methods and approaches, but we're doing something a little more stylized with it. So what we want to do is build this effect here, where we have the flip simulation that's sort of conforming to the shape of our template head, and then emitting bubbles and particles as part of that effect. And it's a little bit different. There's a few differences in how we're going to approach this from doing the martini glass, but it's fun stuff, and I think it's shows how versatile some of these effects can be for doing stuff that's kind of more realistic, or if you want to do something that's more abstract. So let's start with the template head, and want to do some prep with that. So first off, yeah, that's turned off. And let me make a quick select this view. Control 1 will make a quick mark. And go to our build section here. And I'll do Control 2, and that'll set a quick mark for that too. So I can just press 1 on the keypad to switch between them. All right, so let's copy these. Yeah, and anytime you're working with, oops, I think I missed something. Working with compositing, like if you're working with a compositor, the more layers that they have inside that EXR custom stuff that they can use to adjust things in the comp, the happier they'll be. All right. So we're starting with the template head and just clipping it at the bottom here. We don't want the neck. And blasting away the mouth area that we don't want either. Polyfill will give us airtight geometry again, because we want to turn this into a volume. And then doing a match size to make it a little bit bigger. Because this effect is a little bit stylized, we're not actually working with real world units. So really just finding a scale that works for us is what this is all about. So I scaled this up by, I don't know, maybe 5 units, no, 2. And then making a null so we can reference the geometry later on. And then also I'm getting the bounds using a bound SOP. This is a little bit different than the other setup because we want to have different bounds for the flip simulation than we do for all the others, all the particle simulations. So that's why we have that. Make sure we're grabbing our global bounds and our control. So this right here will be our global bounds for any of the particle simulations. And you can see it's just outside the view of our camera. So everything will clip it at that point just for efficiency's sake, and the pyro as well. And then control panel, like I always do, that gives us our frame range. I didn't really do much in terms of adding any tabs for controls, but that's something that you can definitely have a go at on your own to experiment with building that out. So taking our template head and then using thicken to give it some interior faces. We could use poly extrude for that, but thicken seems to work pretty well. Let's just clip that to look at it. So yeah, we have interior faces, and it's not the cleanest. You can see it does get a little bit messy, but for our purposes, that's fine. It's going to work fine for us. And then subdividing that, and then doing a VDB from polygons. And an important thing here is that we do want to preserve holes. Otherwise, we'll lose those interior faces. So if we look at a volume slice here, 0.15, actually, we map this to, yeah, there we go. So as you recall, the VDB from polygons, these exterior band voxels are multiplied by the voxel size. So that means I can get the minimum and maximum from that. And you can see we have our VDB volume here. And I'm going to draw on the screen real quick. So again, negative values right here and positive values going outward. And then outward in both directions here. And then the 0 value is the boundary of our surface. It's the actual boundary. That makes sense?
Yep.
All right. Okay. I'm having a little bit of trouble with my mouse, so bear with me for a moment here. There we go.
No worries. Do you need to restart anything?
It seems to be okay right now. Seems to be all right. Yeah. Okay. So we prepped that, and then we need to do a little bit of further prep on the head, and because we're going to be using a vex function to move particles along the surface, and we don't want to have a whole lot of geometric detail when we're doing that. So doing a separate process here for input into the minpos function, which we'll go over later. So doing a much more coarse VDB from volume, converting it and smoothing it quite a lot. So we get the shape of the head, but not a whole lot of details. And then quad remesh, even though it's in beta, the labs quad remesh, I've found it actually works pretty well for outputting nice clean geometry. So that's been cached and prepped for later use. And then next we need to set up our sourcing. So grab this. And sourcing is going to be very different than in the prior setup. We're not doing a growth sim or anything like that. First off, just making a box and then turning it into a VDB volume and combining it. But we're going to combine it with an intersection operation with the head just to get the base. And that's going to be where we're going to source almost everything from. So reshaping that slightly and then converting it back into polygons. For the flip source, I'm actually adding a little bit of, let's turn this off. Adding a little bit of noise to it. And even though it's kind of a mess, it's for what we're doing, it's going to be fine. It's intersecting, but we're just going to source some flip particles from it, so it'll be fine. And then this will be our pyro source, which is just a plain geometry. So let's do the flip sim next. All right, so in the last one, the last setup, we built the flip sim as a DOP in a DOP net. This setup actually uses the SOP level flip solver, and no particular reason, but I just found like it seemed to be working for me for this particular setup. And again, caching out the points because we're going to source particles from flip points later on. But let's go ahead and dive into a little bit of the settings of what we're doing with this. So to start with, the flip tank, the domain is referencing these flip bounds that we set because we want them to be a little bit tighter to the area that we're simulating just for efficiency. And since the bound doesn't actually output, we can't actually just copy and paste the size values. We actually are using an expression. So if we click on this, you can see using a bounding box expression to find the dimensions of that bound SOP, and then using a centroid expression to get its position. So does it all make sense? All right.
Did you type that in yourself?
Yes. Yes.
Could you just make that really big just for a second?
Sure. Yeah.
I think you can even right click on the word size and bring up the expression. David, do you know what I'm talking about? Just so people see it. That's okay.
Yeah.
So
Well,
people-
hopefully this is visible, somewhat visible.
It's visible. It's an H script VBox function, just so people know that it's an H script function.
Yes, it's an expression function that and this is the syntax that you would use. You'd point it to the path to what you're using, and then the dx size, and you can see dy size, dz size. It finds the bounding box of those dimensions.
Great, thank you.
And then the centroid just finds the center point using very similar syntax.
Those backticks though?
Oh, these aren't backticks. These are actually they are quotations. It doesn't really matter. You can use single or double quotations.
Ah, okay.
Yeah, I know that's a little bit confusing, and that's probably why a lot of people still use double. I've gotten to a habit of just using single quotations.
Good to know.
Yeah. Yeah. And then inside of that, inside of our flip solver, looking at my notes to make sure I'm not missing anything. All right. Yeah. The only other thing is we're adding some surface tension, not a lot, just to give it a little bit of structure. And reducing gravity. We don't want a ton of gravity pulling things down because we want it to fill up from the bottom. And then in the flip boundary, which is where the sourcing is happening, we're bringing in uniform pressure from the from our source here. And what that does is it brings in particles in the direction of the normals. So these values are fairly arbitrary in terms of pressure. I just kind of found what worked in this particular situation. And so, yes, we're sourcing points into the flip simulation. And then in the solver itself, there's not a whole lot that's not default in here, other than I am using the swirly velocity transfer and some oversampling, which closes up some of the holes you might get in the flip sim. And the fun stuff is actually happening inside. If we double click on the flip solver, I'm adding a few things to the force of the simulation. And the main one is this little Vex expression here. So first off, I am referencing the SDF. So the VDB volume that we created from the head is referencing into this as the third input. And then I'm using a function called volume gradient. So finding the volume gradient it's actually super handy. The gradient is just the direction of greatest value, of greatest increase in value. So if I go back here to our volume slice, so we know that we have negative values on the inside of our volume. I'm going to try to draw on the screen again here. So less than 0 here and greater than 0 on the outside of our boundary. So if we find the volume gradient, we're going to get a vector that goes from in the direction of greater value, which is going to look like this. And actually, it's going to look like this too, because we have interior faces here. So now, as I draw these arrows out, what does this look like? It actually kind of looks like normals. So one way to look at the volume gradient is you can kind of think of it as volume normals. It gets you those direction vectors. So going back to the flip sim here, what I'm doing here is I'm finding that volume gradient and then I'm adding it to force. The inverse of it though, it's times -1, and you can kind of guess why. Is we want to add force in the inward direction of our volume. And then there's a multiplier here, which is pushing up pretty high. Again, a fairly arbitrary value for what works. So what that does, it has the effect of pushing everything inward. So if we're sourcing flip at the bottom here, it's going to want to go in every direction, but we've got force always pushing it back into the interior of our volume here with that volume gradient function. And that has the effect of kind of guiding the flip along that surface inside of that volume, if that makes sense. All right, so diving back in here, does that all make sense so far?
I think we're good. Any
At
questions?
the next step.
That's a nice technique. Really cool.
Okay. At the next step here, one of the things that's kind of fun is just to add a little bit of more noise to the force, and that's just in this volume VOP here. I mean, in this pop VOP. I'm sorry. Just adding some anti-alias flow noise, and so that'll give us noise that changes from over every time step, and I'm adding a little bit more to it. Oops. By putting a time expression in the offset in Y. So that just for a little bit of additional swirly motion, and that gives us this kind of chaotic and swirly, but also it is conforming to the shape. So when you're doing things like this, there's going to be some trial and error in finding the amount of force that you want to multiply to that volume gradient, enough to where it's following the shape, but not so much that you're just kind of flattening it out. You do want to have all the fun stuff that the flip sim gives you. And I also have another Vex, another pop wrangle in here that I didn't end up using. And what this does is it volume samples the surface input and then removes any points that are inside of a are, well, in this case, with a value greater than 0. So like that would be anything exterior. I don't end up using this. It wasn't really adding anything, but you could do the opposite. You could say anything that's less than 0, get rid of those points. And it would be, actually, that is correct. You'd want things that are inside of the surface to stay. And then this would get rid of any points that stray outside of a boundary that you could set. Right now it's 0. So that would be the actual surface of the polygon. So if that makes sense, but I didn't end up using it. It wasn't really necessary, but it's a handy thing to have in your back pocket. So yeah, that's our flip simulation. It's really fairly simple in terms of, we could layer up other pop forces on this if we wanted to, but this really did give a nice kind of swirly effect that was basically in the shape of our geometry.
Looks so cool.
So the next stage, any questions on that? We're going to go on to meshing. But anything on that?
So what's neat is that you made a flip solver, and inside that flip solver, you have another solver inside of the pop.
Yeah, a wrangle, running some functions. It's actually not. It's calculating this at every time step of the solver. Right. But yeah, exactly.
Awesome.
Yeah. Okay, and then meshing is going to be very similar to what we did in the other setup. I'll just grab this. Also, a difference in this setup is that we're not advecting the flip simulations. Wasn't really necessary. So here, just taking those flip points, excuse me, and doing a VDB from particles, reshaping them, just some standard process. And you could totally use the flip, what is it called? The particle fluid surface SOP to do this, but I generally find I get better results by chaining together some VDB SOPs. So that gets cashed out, and really some fun shapes. Like I depending on your geometry, you could do some pretty fun stuff. So yeah. And then we've got our pyro advect. Let's go ahead and dive into that.